At the beginning of the 1990s, the global system for mobile communications triggered an unprecedented transformation in the way people communicated. Earlier analog wireless telephony systems, such as advanced mobile phone systems or Nordic mobile telephone, were limited in scope, being country specific and used by only select few. These systems often suffered from poor interoperability and limited user capacity. In contrast, GSM, a global system for mobile communications, represented a global standard designed to facilitate compatibility across borders and cater to a far longer user base. By the late 1990s and early 2000s, GSM had been adopted worldwide and served billions of users during its peak, revolutionizing personal and business communications. This widespread adoption was largely driven by ongoing advancements in telecommunication technology, which led to significant cost reductions for both infrastructure equipment and mobile devices. Affordable devices paired with widespread network deployment made mobile communication accessible to the masses. GSM's architecture, with its scalability and adaptability, also laid the foundation for packet-switched extensions like General Packet Radio Service and enhanced data rates for GSM Evolution, which provided early mobile internet services. These systems are discussed in detail in next lectures, but moreover, GSM served as a precursor to more advanced technologies such as the Universal Mobile Telecommunications System, UMTS, and High-Speed Packet Access, HSPA, which are covered in next lectures. The journey of GSM began in the mid-1980s when the European Telecommunications Standards Institute, ETSI, initiated the standardization process. Despite its origins in this era, GSM remains in use today, demonstrating its robustness and adaptability. While its role has diminished with the rise of 4G, LTE, and ongoing deployment of 5G networks, GSM continues to play a crucial part in modern mobile communication systems, particularly in regions where advanced networks have not yet fully replaced older infrastructure. With the advent of 4G LTE networks, voice communications has evolved through the introduction of voice over LTE. This service allows voice calls to be transmitted over the LTE radio network, providing superior call quality and faster connection times. However, the transition to VoLTE is still incomplete. Many devices, especially older models and some networks, lack VoLTE support. In such cases, mobile voice calls rely on flashback mechanisms reverting to GSM or UMTS networks for call handling. Additionally, the GSM and UMTS networks remain the backbone for voice telephony during international roaming. As of creating this course, only a few operators have extended their VoLTE services to support seamless roaming, leaving GSM and UMTS as critical components for global voice connectivity. Understanding GSM's architecture and evolution is vital for grasping how modern mobile networks function. Over the years, the deployment of GSM networks has undergone substantial changes. Initially, the GSM systems were designed with relatively simple structure aimed at providing basic voice services and SMS. The original architecture comprised a base station subsystem, BSS, for handling radio communications, a network switching subsystem for call routing, and operation and support subsystem, OSS, for network management. As user demands grew and the technology advanced, GSM evolved to support additional features such as GPRS for data transmission, Edge for higher speeds, and integration with IP-based services. Today, even as GSM coexists with more advanced networks, its legacy endures. It continues to be a critical fallback option, especially in rural or remote areas with limited LTE or 5G coverage. GSM's compatibility and reliability make it a valuable tool in scenarios like disaster recovery, machine-to-machine communication, and emergency services. In summary, GSM not only transformed mobile communication during its heyday, but also established the foundation for subsequent generations of wireless technology. Despite the dominance of 4G and emergence of 5G, GSM remains relevant in certain contexts, particularly for voice telephony and basic connectivity. A deep understanding of GSM's architecture, evolution, and practical applications is essential for anyone involved in the deployment and management for mobile networks today. This section will first explore the original design of GSM and then trace the significant enhancements that have shaped its evolution over the decades. Initially, GSM was designed as a circuit switch system, mirroring the structure and functionality of fixed-line telecommunication networks. In this design, a dedicated direct connection was established between two users for the entire duration of call. This connection spanned every interface between all network's nodes involved, ensuring an exclusive path for communication. While this approach guaranteed a reliable and uninterrupted link, it also meant that network resources were locked for duration of the call, even during periods of silence. Over time, advancements in technology and growing demand for more efficient communication methods led to the virtualization of physical circuit switching. Today, GSM networks nodes are typically connected through IP-based broadband connections, allowing for more flexible and efficient resource usage. And here in this lecture, you will also learn about the overview of the traditional architecture of circuit switched GSM networks, while later in this lecture, we will explore the transition to virtualized circuit switching and its benefits. The GSM mobile telecommunication network was initially modeled after circuit-switched fixed-line networks. These systems relied on establishing a direct and exclusive communication path between two parties, ensuring consistent voice quality and reliability. At the beginning of a call, the network would set up a connection between the caller and the receiver, and this path would remain dedicated to their conversation until the call ended. In this illustration, you can see the switching matrix employed in a traditional switching center. This matrix acted as the central component for routing calls, connecting the originating party to the destination party. Once a connection was established, the conversation flowed transparently through the matrix, with the switching center intervening only to clear the connection when the call concluded. And this circuit switch approach was not unique to mobile networks. Fixed-line telecommunication networks of the time also employed similar mechanisms. Initially, these networks transmitted analog signals directly between subscribers, creating a continuous electrical circuit. However, the mid-1980s saw a shift toward digital technology in switching centers, marking a significant improvement in how calls were processed. And in this new digital paradigm, analog voice signals from subscribers were digitized by the originating switching center. The digitized signals were transmitted to the terminating switching center. At the destination, the digital signals were either converted back to analog or processed digitally, depending on the type of subscriber equipment. In countries where integrated services digital network, ISDN lines were popular, the entire transmission process became fully digital. And ISDN allowed for better call quality and faster data transfer rates, as it eliminated the need for analog to digital conversion during transmissions. And the conversion to analog signals occurred directly in the user's phone, ensuring seamless communication. When GSM was standardized, it reused much of the existing fixed-line telecommunication technology, such as switching centers and long-distance communication equipment, minimizing the development costs and leveraging proven technologies. However, GSM introduced a crucial innovation, the ability to wirelessly connect subscribers to the network. In fixed line networks, subscriber connectivity was straightforward, requiring only two dedicated wires per user. And this simplicity was not feasible in mobile environment where users were free to move and change locations dynamically, and GSM had to address several challenges unique to mobile networks. Dynamic subscriber location. In mobile networks, the user's location could change at any time, unlike fixed line networks where a subscriber's physical location was static. GSM required a flexible system to track and manage subscriber locations in real time. And this necessitated the development of mobility management architecture capable of routing calls to a subscriber's current location. Handoff and roaming. During a call, a subscriber might move out of the coverage area of one radio transmitter and into another, and the GSM had to ensure seamless handoffs between cells without disrupting the ongoing call. This required sophisticated software capable of dynamically adjusting the call routing. Switching center modifications. While the hardware of a mobile switching center (MSC) was similar to that of a fixed line switching center, GSM introduced significant software changes. These changes supported functionalities such as subscriber mobility management, call handoffs, and integration with the wireless radio network. And in this figure, you can see how the same hardware could be adapted for fixed line or mobile network use through the different software configurations. Telecommunication equipment vendors like Ericsson, Nokia, Alcatel-Lucent capitalized on this versatility. They offered unified hardware platforms that could be deployed in both fixed line and mobile networks, with the operational role determined solely by the installed software. Virtualized circuit switching. Over the years, the limitations of physical circuit switching became apparent, particularly in terms of scalability and resource efficiency. The rise of packet switching technologies like GPRS and later LTE introduced more flexible methods for transmitting voice and data. In modern GSM networks, physical circuit switching has largely been replaced or complemented by virtual circuit switching over IP-based broadband connections. This transition allows for efficient resource utilization. Network resources are allocated dynamically, reducing idle time during voice calls. Scalability. So virtualized switching can handle higher traffic volumes with fewer hardware requirements. Integration with modern networks. So IP-based systems facilitate seamless interoperability with newer technologies like LTE and voice over IP. The virtualization of circuit switching represents a significant step forward, ensuring that GSM networks remain viable in a rapidly evolving telecommunication landscape. In the 1990s, voice calls dominated communication. However, today, a broader range of internet-based communication methods has taken precedence, with voice calls remaining important but no longer central. These newer services primarily rely on the Internet Protocol to connect users globally. Unlike traditional circuit switching, where a dedicated channel is reserved exclusively for two parties, IP-based communication uses data packets, each containing a destination address. These packets are routed independently through the network, utilizing shared high bandwidth links that carry data for multiple users. And this paradigm shift forced network operators to maintain two separate infrastructures, a circuit switch network for voice communication and a packet switch network for internet-based services. Managing these dual networks proved costly and inefficient. prompting the replacement of the circuit switching hardware in the mobile switching centers with media gateways. And this transformation virtualized circuit switching, enabling voice calls to transmitted via IP packets. And the result was unified IP-based networks that eliminated the need for physical circuit switched infrastructure. This approach, standardized under the term Bearer Independent Core Network (BICN), streamlined operations and reduced costs. But despite this shift, the core functioning of GSM remained largely intact. But the key change occurred in the lower protocol layers responsible for call signaling and voice transmission. Over time, IP-based communication extended into GSM radio network, particularly with the advent of multi-technology based stations supporting GSM, UMTS, LTE, and 5G NR. And today, such base stations typically connect the core network via a single IP link, simplifying infrastructure management. But for mobile devices, the GSM Air interface, the communication link between devices and the network, remained unchanged during this transition. From a user's perspective, the move from circuit switching to IP-based transition was seamless as it primarily affected the underlying network infrastructure.